Hi guys, so in this lecture we'll be talking about melting point, boiling point and their comparison and the comparison of different compounds on the melting point and boiling point. Okay, so let me first define, or let's have first talk on melting point. Okay, so we have two compounds. One is well ordered, or you can say crystalline form or in crystalline state, and another you convert it into a liquid state. So the temperature at which this kind of reaction takes place, when we have a crystalline, we have some compound in crystalline state to convert it into a liquid state, the temperature at which this happens, this is called melting point. Okay, so crystalline, we have charges associated nearby to each other. Okay, so lot of it, or lot of the rate of, or the comparison of melting point depends upon how much strong is the bond between the ions in the solid form or in the crystalline form. Okay, so higher the bonding between them, higher would be its melting point, because we need to provide more energy to the bonds to actually break themselves and loosen them up, so that they reach a state called known as liquid state. Okay, so let us take some example in which we have CS3CO2 minus and Na plus, and we have to compare its melting point with this. Okay, so in this case we have this as the ionic bond is present between CO2 minus and Na plus, and in this case hydrogen bonding is present. How hydrogen bonding is present? Because between two molecules of acetic acid, this is called acetic acid or ethanoic acid, you can call whatever you want to, and hydrogen bonding is present between this oxygen and this hydrogen, and this oxygen and this hydrogen. Okay, so this is basically the hydrogen bonding which is present between them. You can label it like here. Okay, and in between ionic bond is present between CO2 minus and Na plus. So obviously ionic bond is more stronger than hydrogen bond, hence the melting point order would be this would be greater than this one. Okay, let's have a look at this example where we have this and this. So this is trans to butene, and this is cis to butene. So which will have more melting point? This will have more melting point. And why? I'll tell you the reason. Because in this case the voids, or the intermolecular distances between cis molecule between trans molecules of this compound is less. You can see that this can be easily fit into each other in a form of stack. These are all the trans to butenes. Okay, but in a cis form they will have more void spaces to accommodate all the molecules, hence there is a lot of void spaces when we actually pack cis to butene. Okay, so as the void or empty space increases, hence melting point will decrease. So this compound's melting point, or trans butene melting point, would be greater than cis butene. Okay, so we can also say conversely, like more surface area, more is the melting point. Okay, and less surface area, less melting point. Okay, so let us compare between these two. We have this and we have this. So this is obviously trans and this is obviously cis. So in this case also melting point would be of this order. And also you can say about boiling point also, because boiling point also sees the same characteristics as the compare as what we saw in the comparison of melting points of two compounds. Okay, so again the same reason, more surface area, more is the melting point. It can be compactly packed, or the trans versions can be compactly packed, and these have to be packed with more empty spaces or simply voids. Okay, so this completes our comparison of melting points and boiling points. Next we will be starting off with new category of isomerism under stereoisomerism. One we have already discussed about geometrical isomerism some lectures back. Now we are going to discuss about optical isomerism. So if you have forgotten, I'll again remind you with the chart, or the chart which we actually prepared at the time when we were classifying different type of isomerism that is possible in compounds. So under a branch of stereoisomers, we divided this stereoisomerism into two parts. One was configurational or conformational, and another was configurational. So in conformational we studied about amine inversion, and rotation across pi bond. Sigma bond. So these in amine inversion we have seen rotation across sigma bond in the form of conformers we have seen. So this part is covered. Now in configurational we actually subdivided into geometrical isomerism and optical. So geometrical also we have seen. Now what is remaining is optical configurational stereoisomerism. Okay, so let's discuss about optical isomerism. Okay, optical isomerism. Okay, so let us first discuss about important terms in optical isomerism. Important terms which we are going to randomly use, frequently use. So these are chiral center, So what is a chiral center? Chiral center is also known as stereogenic area, stereogenic center, stereogenic center, or it is also called stereocenter, simply stereocenter. Okay, so if we have examples such like this, wherein we have so one more thing is, there is no rule of thumb that chiral center has to be carbon. So chiral center may or may not be carbon atom. Okay, so let's discuss example on the same. We have nitrogen as our chiral center here, and we have four groups attached to nitrogen, namely R1, R2, R3, R4. Okay, so this is the general formula for representing any chiral center. This is the chiral center. Now the groups attached to it would be A, B, C, D. Make it C dash. Okay, so I'm writing some of the examples, and you have to identify whether the given atom or the claimed atom is chiral center or not. So is it a chiral center? No. Is it a chiral center now? Yes. Why? In the cross section, two oxygen were present, so the same atoms were present, and all these are ABCD, right? They are not same by any chance. And the second chance, one was the isotope of oxygen and another was the O16. Okay, let's look at this example. We have so is this a chiral center? No. Why? Because it is sp2 hybridized. I mentioned this is the chiral center with 4 valencies or sp3 hybridization. Okay, whether this is a chiral center or not, no. Why? Because if we take this as a chiral center, the rings here and the rings here are the same. You can take from any carbon atom, they would both be the same. Okay, one more thing, you cannot actually take this carbon, these 8 carbon atoms. Why? Because they have already 2 hydrogen groups attached to themselves. So you can talk about only this carbon atom or this carbon atom, which are both symmetrical. So hence I showed you only one example wherein I took this as the chiral center. Okay, now let's see whether this can qualify for our definition of chiral center or not. So you can see definitely this and a lone pair are different groups on nitrogen, but you can see that this can get involved in resonance with oxygen and can form a resonating structure with minus charge on oxygen, double bond here with a positive charge on itself. So you can see this is a sp2 hybridization. Hence this does not qualify for being a chiral center. Okay, so it's not a chiral center because of sp2 character. Okay, so with this we end our lecture, and in the next lecture we will be seeing some more examples on the chiral center. So till then, good luck and goodbye.